Hello and welcome. Today I'm going to talk about some new seismological findings on Mars. Martian crustal structure can reveal how the red planet differentiated and evolved over geological times. In 2018, NASA InSight mission sent a broadband seismometer to Mars. After the successful touchdown of the InSight lander, more than 1,000 marsquakes have been recorded, and many seismological methods have been applied to provide the first seismological constraints on the crustal structure on Mars beneath the InSight lander. Now we know that there is a first layer in the crust at around 10 kilometer depth. And at 20 kilometer depth, there is another second layer. And probably there will be a third layer at around 40 kilometer depth. Our focus is the first layer, or layer 1, above 8 kilometers. This is because the S-wave velocity within this layer is really low, less than 2 kilometers per second. Here, figure A shows the model parameters in this layer. The x-axis is the thickness of the layer, and the y-axis is the average S-wave speed. I want to note that those models are from a previous receiver function study because they only have one station to perform the receiver function analysis. Therefore, there will be pretty large trade-off between those two parameters. But nevertheless, most of the models show a S-wave velocity smaller than 2.0 kilometers per second. So our goal is to further constrain the properties of the first layer. And the method we use is called the S-reverberation. Figure A shows that besides the direct S-wave in black, there is another SH reverberation in red between the free surface and the base of the first layer. Then we can use the differential travel time between the S reverberation and the direct S wave to constrain both the thickness and the average velocity of that layer. And we have found such a phase in the real seismograph. For example, figure B is an example of event 235B. At around 10 seconds after the direct SH wave, there is another smaller phase. And we shift this smaller phase 10 seconds earlier and amplify its magnitude by negative 3 times. The shifted phase is shown in red. Now we could see that the smaller phase originally at around 10 seconds after the shifting and the amplification of the amplitude, the waveform of this smaller phase, the red one, fitted the original SH wave, the direct SH wave really well. The cross-correlation coefficient is more than 0.8. So now we know that this smaller phase can be a S-reverberation, as I showed in figure A, or it could be a depth phase of this event. We have checked all the high-quality marsquakes, and we found that almost all of them show a similar smaller phase at around 10 seconds after the direct SH wave, and almost all of them show a high similarity compared with the direct SH wave. Therefore, we think that this phase, or this consistent phase from all events, is less dependent on the focal depth of the marsquakes. Instead, it should come from a common structure feature, which is the S reflection in between the free surface and the base of layer 1. So we can use this differential travel time of about 10 seconds to constrain layer 1. Still, the heat map in figure A are model parameters in layer 1 from a previous receiver function study. And from our constraints of the reverberation analysis, we have provided an independent constraints on the model parameters shown as the blue contours here. Surprisingly, the model parameters constrained from our reverberation analysis do not intersect with the receiver function derived models. And more interestingly is that the S-wave speed of our derived models are systematically smaller than the receiver function derived models. And we propose that this inconsistency comes from the presence of seismic anisotropy in this layer. This is because the receiver function models are mainly reflecting the S-wave wave, which is a vertically polarized S wave, and the SH reverberation are mainly reflecting the velocity of the horizontally polarized SH wave. We can also calculate the anisotropy coefficient cosine, which is SH velocity over SV velocity then square. So the average value or majority of the values are smaller than 1.0, indicating that there are significant discrepancies between those two SV velocities. To generate this observed seismic anisotropy, we have proposed a model. First, there is an isotropic matrix, but when there are some isotropic oblate intrusions, this combination is no longer isotropic. Instead, it is transversely anisotropic. And we found that this intrusion model could reproduce the observed S-wave anisotropy. So we know that this model setting could generate the observed anisotropy, but the question is if there are those east-west oriented intrusions on Mars. The answer is yes. Figure B is the infrared image on Mars near the InSight lander, and we could see that there are some north-south trending wrinkle ranges. And those wrinkle ranges might indicate the presence of regional compressive stress. And those compressive stress could generate those east-west oriented fractures. Another interpretation is that those intrusions actually are igneous intrusions. For example, near the InSight lander, there was a really large degraded crater, and the diameter of this crater is almost 200 kilometers. When this crater was generated, the impact melting can generate radial decks, and the direction of this decking are just along the radial direction. Notice that our InSight lander is located to the west of this crater, so the direction of the radial decks are just along the east-west direction, which is really consistent with our proposed model. So to conclude, we made the first detection of the S-wave reflection generated from layer 1 on Mars. And with this phase, our derived S-wave velocity is systematically smaller than another S-wave velocity constrained from the P2SV receiver function. And we propose that this inconsistency comes from the existence of seismic anisotropy in the first layer. Modeling results show that dry or liquid filled cracks or fractures and igneous intrusions could generate the observed anisotropy. But all those intrusions should be aligned roughly along the east-west direction, and porosities in layer 1 is required for this mechanism to generate the observed anisotropy. Thank you.